Hello, my name is John Tyler. I'm a senior lecturer in electrical engineering here at Texas A&M University, and my goal today is to talk to you about electric circuit theory to get you ready for your EIT. The references I used in preparing this talk, a couple that you've probably seen. This is the reference handbook from NCEES. There's a review manual that I understand you all have copies of, and I use this for the outline of my talk. Also, I'd suggest that if you still have a copy of the textbook that you use to study your course in electric circuit theory, that would be a wealth of additional problems to look at. What we're going to talk about today is not going to go into the great detail that you probably discuss these topics in your regular course, but it's going to be enough to give you the background you need to do well on your EIT. What I have on this first sheet is an outline of the talk. We're going to talk about fundamental definitions, resistive circuits with DC sources, and then we're talking about solution techniques here in section 3 using resistive circuits, but these solution techniques also apply to transient and AC circuits. I'll mention capacitors and inductors, their mathematical models, and also their physical properties. We'll use capacitors and inductors and resistors together to create circuits that have transient behavior. And I'll go through the analysis of how do you set up and solve a first-order transient problem. We'll move on to AC signals, just a general overview of the terminology of AC waveforms, and then how AC signals appear in circuit analysis problems. We'll handle those with the theory of phasors, and that's going to require a brief review of complex algebra. Finally, last topic will be operational amplifiers that have both DC and AC applications. So to start off with, I want to review some things that you probably already know about from basic physics. You knew about these before you went into your first circuits course. And that was the fact that charge is a property of matter. And so if you have an isolated charge, and say this has positive Q value, radiating out from that charge are electric field lines, and it's by this means that electric charges interact with each other, because over here if we have a negative charge, it's going to feel an attraction to this positive charge, and the way we can calculate that is to figure out how strong is the field, the electric field, due to this charge at the location of this charge. And that's where we get into Coulomb's force law. You might recall that this is a vector force. It's a vector direction from charge 1 to charge 2, and then the magnitude of that is the product of the charges divided by the separation between them. And there's a multiplication constant just to get the units right. It's alternately called K and K sub C for Coulomb. What we're going to do now is show where the electric field comes from in this Coulomb force law picture. First I need to go back to the diagram and define my vector direction. The A sub 1, 2 is a unit vector in the direction pointing from the source of the field to the test charge, in this case the minus Q. So this could be our Q1, this positive Q could be Q2. And down here in the equation, what you can do is isolate and say, well, Q1 is the charge that's feeling the effect of the field. So let's isolate that out in front, Q1, and then we'll say A12 is the vector direction, Q2 over R12, and I better fix my equation with a square right there. And there's the proportionality constant. Well, what we can do really now is figure that this is a separate vector and define that as a vector field, the electric field. And it makes things a lot simpler to view the problem this way, that you have an electric field due to source number 2, and it's affecting charge number 1. So anytime you want to calculate the value of the force between these two charges, you would just put in a value of Q1 and Q2 in coulombs, R in meters, and the correct constant which you have in your reference manual. This point of view of the electric field is much easier, and that's the one that we're going to expand on in the next slide. There is a section in your reference manual about electrostatics and electric and magnetic fields. The problems that I looked at, the sample problems from the exams, really don't go into a lot of depth in this field, so I'm going to touch this very lightly. Just remind you that there are two fields. This one is called the displacement field. It's also called the electric flux density. And let me abbreviate density. The E is the actual field, the electric field intensity. And normally we just make that an abbreviation. Instead of calling it electric field intensity, we just abbreviate that to electric field. Now in circuit analysis, we're more interested in voltages and currents. The electric and magnetic fields are really in the purview of another field of electrical engineering called electromagnetics. In circuit theory, we generally are interested in the effects that the electric field has on positive test charges in circuits. So what I need to show you now is the relationship between an electric field and the voltage, or potential difference. So voltage is also referred to as potential difference. And that's actually the key to understanding the relationship between voltage and electric field. Let's go back to our positive charge plus Q. It's got field lines radiating out from it, all of them originating on the positive charge. If it's just an isolated charge, those field lines are going to go off to infinity. And now let's imagine that we have a little positive test charge, let's call that Q naught, and we move it from position 1 to position 2 by some path. Well, at position 1, the charge Q0 is feeling a stronger force than at position 2. So if we're moving from position 1 to position 2, we're actually feeling a difference that's, we're moving the charge in a direction that it wants to go anyway. If Q0 is a positive charge, it's feeling a repulsive force from the origination of the field. And so we're moving this charge in a direction that it wants to go anyway. That would be a difference in potential energy. We're allowing the Q0 charge to lose energy in going from position 1 to position 2. Now if we reverse that and said, well, let's say if position 1 is here and we want to move along some pathway to get to position 2, which is closer, and we're going this way, we have to work against the field to go from potential 1 to potential 2. And that's where the idea of potential difference comes in. It's a real nice way of bypassing all of the detailed theory and the mathematics of the electric field. We can simply summarize the effect of this charge as saying there's a potential surrounding it, that each point in space has a potential energy associated with it, and that if we go from, say, position 1 to position 2 along this path, we're feeling a difference in potential energy. And that difference is expressed in volts. Now just as a side note, you'll also see in your reference materials the symbol script E, the symbol lowercase e. They're all referring to the same voltage concept, and you can tell from the context of the review material, if it refers to an E in volts, you know that that's a voltage. What I'm going to use this morning is usually capital V if it's a constant or DC voltage, and this lowercase v, canonically in the normal presentations, lowercase means that it's time dependent. In a lot of cases I'll go ahead and make an explicit time dependence here, but even if you don't see the functional dependence on T, lowercase v means that it's dependent on time, uppercase V means it's constant. Well, now, by analogy with electric fields, there are also a lot of the same things going on with magnetic fields. Again, judging from your review and reference material, this subject isn't covered as much in detail even as the electric field concept. So let's touch on this one briefly. I mainly want to remind you of some things that you know about that are going to help you understand inductors and capacitors. Okay, the same sort of relationship exists here. B is called the magnetic flux density. H is related to it by constant is the magnetic field intensity. And there's a relationship between them that says B is just a multiple mu times H. This same relationship exists between the electric flux and the electric field. In fact, if I can go back to that page for just a second, that's something I meant to include right here. Flux is equal to a constant times field. This is called the permittivity, which is an electric field constant. In the analogous equation for magnetic field, mu is called permeability. And this gives us a way of approaching magnetic interactions in circuit elements. If you just remember the way that bar magnets work, you'll understand the basic theory. You have a north and south pole of a bar magnet, and the same field line concept applies, only these field lines are always closed on themselves. Magnets always come to us in pairs of north and south poles. If I broke this magnet in half, I wouldn't have a separate north pole and a separate south pole. I'd have two new magnets, each with their own north and south poles. But as you know from playing around with toy magnets, that if you try to bring the two north ends of two magnets together, you feel a repulsive force. And the same fact is going to be true when we look at the magnetic field effects in electric circuits. So what we could do is set up a calculation, if we were interested in it, to calculate exactly how strong a force in newtons is felt between these two magnets, a certain magnetic field strength at a set distance. Right now it's just enough to remember that if you have like poles, north and north poles coming close to each other, they're going to repel. Unlike poles attract each other, north and south. So it's very similar to positive electric charges and negative electric charges. Attracting and repelling. Well, again, this is a little bit too elaborate for routine use in circuit analysis. What we want is some laboratory scale effect, and in circuit theory, the effect we're looking for due to these fields is the effect on currents. There's a relationship between magnetic field and current. It says if we have a conducting wire that has in it a current I, that wire is going to be surrounded by magnetic field lines. Now, I'm going to draw a couple here, but you'll have to imagine that this wire is completely surrounded by magnetic field lines. And this is the magnetic field B equal to mu H that we talked about just before. And if you were looking at down the axis of the wire, you would see these magnetic field lines as completely closed circles. One thing to keep in mind is the famous right-hand rule, which says the following. If this pen is indicating the direction of current flowing this way, what I can do is line up the thumb of my right hand with that direction of current, and then the fingers of my right hand curl around. If you watch it, the pen is going away from the camera, my thumb is following the direction of the current, and the field lines are wrapping around according to this right-hand rule fashion. So you can see that same thing here on the screen. If you just imagine that this is the point of an arrow coming up, then your right-hand fingers would curl around in this counterclockwise direction. Well, there's an immediate practical application and a basic bit of theory involving magnetic fields. It's due to Faraday. It's called Faraday's law. And Faraday's law simply says that you get an induced voltage if you have a time-varying magnetic flux. Okay, magnetic flux is just a way of describing how many field lines are passing through a particular area in space. Magnetic flux, in turn, is defined as the surface integral of B over an area. And here's our magnetic flux density again. In a simple case, you would have BA, and if this dot product indicates that you take the magnitude of the vectors and multiply by the cosine of the angle. In many practical applications, in the diagram I'm about to draw, that angle would be 90 degrees anyway. So that factor disappears, and what you're left with is simply a product of B times A. And this is definitely a special case, but it's pertinent to the motor that I'm going to describe to you. Well, now it's clear what happens if you substitute the expression I just got for phi into this equation, the Faraday's law. You have a v of t that's equal to the time derivative of b times a. So if we can contrive to either vary the magnetic flux density, or the area with time, then we will achieve an induced voltage. And this is the basic idea of how motors work. So let me elaborate on that a little bit with a diagram. Imagine that we have a strong magnetic field, north and south poles indicated in here, and there's an area in here where there's a pretty strong magnetic field. So let's just draw a couple of representative field lines. Here's our magnetic field. What we can do to vary the cross-sectional area is have a loop of wire that comes into this region of magnetic field, forms a loop. Okay, now to imagine the geometry here, this is a circular piece of wire that you're looking at on an angle, and I've left enough room between the poles of the magnet that I can take and rotate at a frequency omega. I can rotate that coil of wire, so the wire is going to be spinning around this way, and as it does, you can tell the cross-section of this loop of wire is alternately going to be intercepting a lot of field lines, or when it's 90 degrees to the field, it's not going to intercept any at all. And that's going to vary the effective area of this loop with time. So what we can get by setting up some brush contacts here, we can get a voltage that varies with time. And in fact, that voltage variation with time is going to be exactly proportional to the cross-sectional area as a function of time. And if we're rotating the coil of wire at a frequency omega, what we get is a sinusoidal voltage that also has a frequency omega. Now, you already have an intuitive idea and probably some memory of what frequency is. I'll do a thorough review of all the terminology of AC signals when we get to that part of the session. But I just, at this point, wanted to indicate to you that all of this theory of magnetic and electric fields actually has some pretty practical application. This is the basic idea of motors. If you're converting mechanical energy, the rotation of the coil, into electrical energy, that's the voltage. That's one way of looking at this arrangement. Or you can say, let's inject an AC signal into the same apparatus, so we're putting electrical energy in, and that causes the coil to rotate in the presence of the magnetic field. That's the basic idea of a motor. If you're converting electrical power into mechanical power, that's a motor. The same basic technology works for motors and for generators. Well, continuing with our review of basic terminology and the fundamentals, in an electric circuit, which is simply a path for electric current to flow through an arrangement of elements, for each component, you're going to lose a little bit of energy as those charges go through the corresponding devices, and that loss of energy is characterized by a quality called resistance. Resistivity is the related concept, and what you have to imagine is simply that this is a cross-section of, let's say, a piece of wire. Now, you probably all know that the electron is the mobile charge carrier. We characterize the flow of electrons looking at the basic physics of how the properties of the materials work, and then for our current in our circuit analysis, current is the flow of positive charge, so what we do is figure out physically what's happening with the electrons and decide which way they're moving, and then conventional current is the flow of positive charge. It simply goes in the opposite direction. And as you know from material science, any material is going to have an arrangement of nuclei and surrounded by clouds of electrons that are bonded to those nuclei. That means that this electron trying to go through this material is going to alternately bump into some nuclei, bounce around, it's going to hit some electric fields due to the electrons, and it's not going to have an unimpeded flow through this material. The reduction of energy as the charge goes through the material is characterized by this quantity resistivity. And once again, this is the basic the theoretical level. What we would like is to have a laboratory scale manifestation of that, something that we can grab hold of a little bit easier, and that's where the idea of resistance comes in. If you take a block of material and you know its resistivity rho, you make that block of material cross-sectional area A, and you make it of a length L, then this equation gives you the resistance of this element. So you can be looking at a circuit composed of resistors. Each of those resistors has a geometry similar to this, and you can calculate a resistance in ohms. Either spell it out or use the symbol omega. And the resistance in ohms is related to the length in the cross-sectional area. Now, knowing this model for the resistor helps you remember how series and parallel connected resistors behave. If you had another block immediately following this one, if it happened to have the same cross-sectional area, then what you can imagine is that you're getting the same resistivity. If it's the same material, if it's the same size object, then for twice as long a path, you're going to get twice as much resistance. And that's a nice way of remembering that series-connected resistors add algebraically. Likewise, if I had a parallel path, then I would be increasing the cross-sectional area, and as you can see from the basic equation, if the area goes up, the resistance goes down. So we'll see this again in just a few minutes when I talk about series and parallel connected resistors. But as you can tell by now, I like giving you some mathematical and also physical intuitive pictures to keep in your mind to help you understand the equations. The review materials have all of the equations, and there is a certain amount of just basic knowledge that you have to know when to apply certain laws. But I think it also is very useful to understand the background of those laws and where they come from. Well, that's probably the end of our brief survey of the basic physics of charge and fields and how they apply to the laboratory scale circuits. What I want to do now is turn to the basic definitions that apply to circuit problems, the kind that you see in your reference material. In order for charge to flow through a circuit, there has to be some kind of source of energy. And what we have are voltage sources. Could be of the battery type, which is a fixed DC source. You'll see it labeled with either some named amount, so say 5 volts, or it could just have a voltage variable. Thing to remember about this symbol is that the long bar indicates the positive terminal, the short bar indicates the negative terminal. You have alternately a symbol. It's a circle with plus and minus sign inside it, and that may be labeled with something like V1. Okay, and then somewhere else in the problem statement you find out V1 is equal to 2 volts. Well, this symbol represents a voltage source, and the positive and negative terminals are easy to read off. If you want to be real elaborate about it, you can go ahead and add plus and minus signs. This symbol is very useful also for AC and any other time-varying signal. You can represent a voltage source with a time-varying amplitude with a lowercase letter. So you might see in your literature a V of t is equal to 2 cosine 3t. Well, again, notice the use of the lowercase letter for something that varies with time. And the similarity here between these two symbols is intentional. The idea is to show you that whether it's a DC source or an AC source, the circuit is going to respond according to certain circuit laws, and you can set up and solve problems with the basic idea of voltage sources, regardless of what kind of source you have, constant or time varying. Now, for a current source, the best way to understand this is by analogy with the voltage source. First thing is just to define the symbol. It's the same open circle that you see for a voltage source, but you're given an arrow to indicate the direction that current is flowing. If you see that labeled with a constant, then that's probably a DC. So something like there's a 3 amp source that guarantees 3 amps will flow through this wire regardless of what circuit is connected to it. Similar to the way that you think about a 5-volt battery connected to a resistor is going to create a certain amount of current in the battery. Well, if you connect a different resistor, you get different current. Down here for the current source, it's always going to be the same amount of current. Depending on the resistor you connect to it, it might give you more or less voltage. And we'll come back to that concept when we see these sources in some circuit problems. There's another possibility, of course, analogous with what we talked about earlier, and that's that this might be a time-varying I of t type source. And you might have some defining equation that says this is 4 cosine of 800 pi t, just numbers off the top of my head. The current here is going to be measured in amps. Voltage, we've already mentioned, is measured in volts. And you do have a table of units and constants in your reference material, so you should just familiarize yourself with that table and make sure you know all of the appropriate conversions. The basic concepts of sources then and resistors gives us the entry point to DC circuit analysis. The first thing to point out about DC circuits, or any circuit in fact, is that they, again, obey the basic laws of physics. A first semester physics course teaches you about how energy is conserved and how charge is conserved. What I want to talk with you about now are the Kirchhoff laws. These are the circuit laws that have to do with energy conservation and charge conservation. Starting off with the Kirchhoff's voltage law, or better known as KVL. This says that the sum of all the voltages around a particular loop are going to be 0. Now, what does that mean? If you have a block here, and I'm going to be deliberately vague about whether these are sources, resistors, capacitors, doesn't matter what. If you have all of these circuit elements connected together in a circuit, which is just a complete path for current to flow, and you know that this element has voltage V1 across it, this element has voltage V2 across it, and so on. And this one, let's say, is V4. Then what you can do is sum up all of these voltages. And there's an alternate way. There are actually two ways. In fact, I'll continue with the current law on the next sheet. Need more room for this. One way is to start at a particular node and say, let's go around this loop in a clockwise fashion. So let's go around the loop this way. Going through the first element, I pick up V1 volts. Through the next element, I pick up V2 volts, and so on. And the Kirchhoff law says this has to sum to 0. Well, in a way, what I've just revealed to you by my terminology is that V1, if I'm picking up energy going through V1, that must be a source. And V2, with a plus to minus this way and a plus to minus this way, we're losing energy. And so, in fact, I need this equation isn't quite right, because I don't just total up V1, V2, V3, V4. I have to pay attention to the polarities. So one thing is that you can tell yourself, okay, every time I'm going through an element, if I'm going from lower to higher potential, then I must be increasing my energy, so I could call that a positive term and call all the rest of these negative terms. What I prefer to do, and you can either try this or not, I'll give you an alternate way to look at it, which may match the way you've done it before. I like to just label all the polarities of the voltages and then simply let the circuit tell me how to write the equation. Start at this node, and I know I'm going to run around all these elements and write down a voltage term for each one. Whether it's a positive or a negative term is dictated by which sign I bump into first. If I'm going around the loop clockwise and I get to element number 1, I bump into a negative sign first, so I know I need a minus sign there. For these other elements, I'm bumping into positive signs first. As you go around, you always hit a positive sign. If this were an actual circuit, what I might have in here is a battery and 3 resistors. And the way that you may have learned this material before is to say, well, for element 1, I'm increasing my energy, so I write that with a positive sign. And for all these others, they're resistors, and so I'm losing energy. And so I write all those down with minus signs. Now you can see we wind up with the same equation. It's just the two equations are different by a minus sign. You just take this equation, multiply through by minus 1, and you get this equation. The reason I'm a little reluctant to use this in my discussions with my students is that what if these elements happen to be capacitors or inductors? We're going to find out in a while that capacitors and inductors have the ability to store energy, which means that I might have to change the polarity if this becomes a different element. It's much easier to go ahead and define an assumed voltage for each of these and then write down the Kirchhoff voltage law according to the sign convention that I just mentioned. So you can either do it this way, which is what I've just described to you, or you can do it the more conventional way, whichever gets you the correct equation. In both cases, what we're saying with this Kirchhoff law is that if I'm a positive test charge and I make my way through this circuit, I'm going to gain some energy going through this element, I'm going to lose energy going through these elements, and by the time I get back to my starting point, I better have lost as much energy as I've gained, otherwise energy conservation is not true. And of course, electric circuits do obey all the basic laws of physics, so what we're looking at is energy conservation for circuits. That's really all the Kirchhoff voltage law is. Okay, what I want to do next is describe to you the Kirchhoff current law. The current law has to do with charge conservation. Now, just as the voltage law has to do with loops in circuits, the current law has to do with a node in a circuit. A node is simply a place where several connecting wires are joined together. These could be coming from various components in the circuit. A node in a circuit diagram is usually indicated with the heavy dot, like I'm showing here. That's supposed to remind you of a bead of solder, that several wires have come together and they've been soldered together. If I have a current I1 in this wire, a current I2 in this wire, I'll just go around. Doesn't matter which direction these currents are. And the statement of the current law is that the sum of all the currents around the loop, the sum of all the currents into the node have to sum to 0. So if we have a 1 to up to n, I sub n, all those currents sum to 0. And just as we had to pay attention to the polarities of the voltages for the voltage law, in the current law we have to pay attention to which direction the current is going, into the node or out of the node. Once again, it doesn't really matter which algebraic sign we assign to the concept of going in or going out. So let's say that we want to call currents going into the node positive. What we would write is a plus I1 minus I2 plus I3 plus I4 and then minus I5, all equal to 0. And of course, if you wanted to use the other convention, which is let's let currents going into the node be negative, you would just change all the plus and minus signs here, multiply this equation through by minus 1, and you still have a true equation. This is very useful if you know 4 of these currents, then that allows you to figure out the 5th one. Let's say in this situation maybe I2 is an unknown current. We can set up an equation that says I2 has to be equal to I1 plus I3 plus I4 minus I5. It's just moving the I2 term over to the other side of the equation. And finally, the other way of looking at the Kirchhoff current law is just to say that the sum of all the currents going into the loop have to equal the sum of the currents leaving the loop. So we could summarize by saying I1 plus I3 plus I4, those are the currents going in, have to equal the sum of the currents going out, I2 plus I5. Now this KCL is true for an isolated node. It's also true for any sub-circuit within a larger circuit. And what we might see in some of our application problems is that you'll have a fairly elaborate circuit with lots of interconnected elements. And what you can do is simply take a dotted line, either mentally or draw it on the circuit diagram, and surround a sub-circuit within the middle of the circuit with a dotted line. And then notice the currents going across that dotted line. The sum of all the currents going into the dotted region have to equal the sum of all the currents leaving the dotted region. So the current law applies either to an isolated node or to this surrounded subcircuit that's also called a supernode. Well, the last topic in our fundamentals review is electric power and energy. What you have is power in watts. Now you've seen me use this symbology a couple of times for all these notes. The square brackets indicate SI units. And so you'd read this statement as power is measured in units of watts. Energy measured in units of joules. What we have in electric circuits, power is the product of voltage times current for a particular element. So if you have another one of these generic blocks in your circuit diagram, if you know there's 2 amps in this wire going that way, if the voltage is 3 volts with a higher to lower potential, then I would say that this element is dissipating 3 times 2 or 6 watts of power. I know that it's dissipating because this current is going from higher to lower potential. That means a positive test charge going from this side of the element to this side of the element would be losing energy. If the polarity were reversed here and the charge were going from lower to higher potential, that would be indicated with a negative 6. That shows power being generated. And in fact, the idea of power balance is that the total amount of power generated has to equal the total amount of power dissipated. If we think purely in terms of resistors, that means if we have a battery, say with 5 volts, and we have 2 resistors, we'll make the arithmetic easy here, with a 2 ohm resistor and a 3 ohm resistor. This battery is going to cause positive charge to flow clockwise in the circuit, and anticipating, in a later slide we'll review again Ohm's law. That's probably the one thing about electric circuit theory that everybody already knows, and that's V is equal to R times I. The point related to power balance is that if you notice the polarity, as I said on this battery symbol, plus to minus like so, and for a resistor it's always positive to negative. The current is always going to flow from higher to lower potential through a resistor. That means, and we'll get into the exact details of how you calculate power for resistors, but for now, this concept of power balance means that if I'm gaining energy going through this battery, I also have to lose energy going through the resistors. If your problem statement is simply calculate the amount of power generated by the battery, all you have to know is how much current is in there. And you probably can figure out from knowing Ohm's law that this will be a 1 amp current, and 1 amp for 5 volts is going to be 5 watts worth of power. So very quickly we could calculate 5 watts generated by the battery. That means that we would also have to dissipate. We know how much power is going to be dissipated by all the resistors in combination. But now if we want to know about the resistors individually, how much is this resistor dissipating, how much is this dissipating, we'll have to go into the detailed equations of power for resistors. And that's our next topic. Well, now that we've finished our review of the fundamentals, it's time to get into some actual circuits. And to start off, remind you again that Ohm's law says for a resistor, the voltage is proportional to the current, and the constant of proportionality is R. And I just want to remind you at this point, so we can understand series and parallel resistors better, you've got the rho L over A model to remember. That's resistivity, the length of the resistor, and the cross-sectional area. And remembering those two parameters and how resistance goes proportional to length and inversely proportional to cross-sectional area is going to help you remember the series and parallel formulas that I'm going to give you. The circuit symbol for the resistor is some jagged lines labeled with either an element name like this or the actual value of the resistor. You'll see these multipliers. This is also in your reference material. You've got the most common ones for resistors would be K for kiloohm and M for mega ohm or megohm, 10 to the third and 10 to the sixth respectively. Now remember from a few minutes ago, power in an electric circuit element is V times I. But now from Ohm's law we can substitute for either V in favor of I or I in favor of V. So we have a couple of different formulas for power in a resistor. We can take the current and instead write it as I is equal to V divided by R, and wind up with V squared over R. Or, alternately, we could take and substitute R times I for voltage, and that gives you R I squared. Or you might know it better as I squared R. The point here is that if you only know the voltage across a resistor and its resistance, and your goal is to calculate the power, you don't really need to take the time to calculate the current. You don't always have to go to the VI formalism to calculate power. If you know the voltage for the resistor and its resistance, you can get the power right away. And likewise, if you only know the current and you don't know the voltage, you can get the power from this formula. Well, now resistors in circuits are usually in combinations that can be identified as series combinations or parallel combinations. And I want to review with you now how to combine resistors. We have series connected resistors. Let's use a set of 3 for just a concrete example. But the same idea holds true for more resistors. And remember, our resistor model says that the resistance of an element is proportional to the length. And so if we have these 3 resistors effectively increasing the length of resistive path that charge has to go through, that means the resistance should increase. And in fact, if we wanted to take this circuit and replace it with an equivalent resistance, Req, then the way you would calculate Req is take the sum of R1, R2, and R3. If you have a special case of a known voltage, and let's just go ahead and use the generic voltage source symbol, and two resistors, immediate application of this series connection gives you one of the most useful rules or circuit analysis tools in your toolbox, and that's the voltage divider, which is concerned with calculating the voltage across one element in a series of series-connected elements. Well, from the Ohm's law and the equivalent resistance, we can calculate the current going through the source. Let's call this I sub S. We know that IS is equal to V over Req, where Req is the equivalent resistance seen by that source. So what you imagine is that you replace this combination of resistors with its equivalent. From the series rule, we know we just take R1 plus R2. So this would be V divided by R1 plus R2. All of these elements are connected in series, so they all share the same current, IS. That means the current going through resistor R2 to create voltage V2 is also IS. So we can write V2 is equal to R2 times IS. But all we have to do now is substitute this expression for IS into this equation, and we find that V2 is equal to the voltage source times the ratio R2 divided by R1 plus R2. Now that gives you a real handy equation for applying to lots of circuit problems where you already know the voltage across the whole branch, and you're not concerned with calculating all the voltages for all the resistors in the series. You just want one of those resistors' voltages. Well, you can use the voltage divider to calculate that. So if I know the value of the source voltage V and the resistors R1 and R2, I can substitute here on the right-hand side and calculate that value V2. There are similar equations for resistors in parallel, and that leads to another circuit analysis tool called the current divider. I want to turn to the derivation of that now. First, let's talk about resistors in parallel. And once again, I want to use just three resistors, but the extension to more resistors in parallel should be pretty obvious. If you have R1, R2, and R3, and what you want is an equivalent single resistor, Req. Remembering that resistance goes inversely with the cross-sectional area, what I'm presenting now to a charge flowing through this network to get from the upper node to the lower node in this diagram, that charge is going to have a greater surface area to travel through, and so it's going to experience less resistance. With all three of these resistors in parallel, we should get a number over here for Req that's less than the smallest of these three. So, for instance, if this were a 1 ohm, a 2 ohm, and a 3 ohm, even before calculating it, I know that the Req is going to be less than 1 ohm, because that's the smallest of the three resistors. That's a good thing to keep in mind when you're checking your calculations. Well, the equation for Req is to take the inverse of the sum of all the inverses So if I know the values of R1, R2, R3, I invert all those values, add up all the inverses, and then invert the total result. Now if you have two resistors in parallel, that takes on the special form 1 over R1 plus 1 over R2 inverted. And you can do the intermediate algebra here to show that what you get is the product of the two resistors over the sum. And this is a useful, handy expression. It's the product R1, R2 divided by R1 plus R2. And you can tell from the units, what you get upstairs would be units of ohms squared, and downstairs you get units of ohms. So everything works out nicely. This is an expression for resistance. I just want to caution you, and the reason I mention these units is to caution you against extending the special case rule to more than 2 resistors in parallel. I've seen this mistake on a lot of exam papers. 3, 4, 5, and 6 resistors in parallel. Don't even want to write the equation down, but students have taken the product of 4 resistors divided by the sum of 4 resistors. If you just think about the units there, that's ohms to the 4th divided by ohms. That gives you something called ohms cubed that I have no idea what it means, except that it's obviously a mistaken application of what looks like a general rule and is really just a special case. So if you have this rule firmly in mind, that's fine, as long as you only ever apply it to a case of 2 resistors in parallel. Okay, for the current divider, we have an arrangement of 2 resistors in parallel, and we have a known source current coming into these parallel branches. So let's call this IS. We have resistors R1 and R2. And let's say that we're interested in finding the current I2 in terms of these other known quantities. The source is assumed to be a known value. R1 and R2 are known. What you do is apply the following rule. It says, just like the voltage divider, this portion of the current is going to be a fraction of the source current, and that fraction is given by a resistance ratio. And the denominator looks exactly like it did for the voltage divider. But what you have to keep in mind about the current divider is that the resistance that goes upstairs here to complete the expression is the resistance of the other branch. So if I want current I2, I put resistor R1 upstairs. And it's fairly easy to figure out why that would be the case. Let's imagine an extreme example where R2 is 1 ohm and R1 is 1,000 ohms. Well, if I'm a charge that's part of this current and I get to this node, I have a choice of either going through a very low resistance path or a much higher resistance path. Well, the majority of the current is going to want to go through the low resistance path. So that's why if the R1 value increases, that's going to increase the amount of current through the other branch. Likewise, if I wanted to get I1 is going to be equal to IS times R2 divided by R1 plus R2. And just so you won't think that I1 has anything to do with that arrow, let's put a box around that. So the current divider is an application of 2 resistors in parallel. Voltage divider is an application of 2 resistors in series. Now, just as we have equivalents to resistors in series and parallel combinations, we can also talk about equivalent networks. First, let's define the term network. Is just an interconnection or a circuit of sources and other elements. Now that could be, in the case so far we've just been talking about resistive circuits, but these other elements could also include capacitors and inductors when we can include those in our networks. What you imagine is that there's some, say arbitrarily complicated network over here, a couple of resistors. Okay, and I have a voltage source here, and let's name all these resistors R1, R2, R3, R4. If we're interested in calculating the current through resistor R4, it's really only necessary to know the equivalent network for this portion of the circuit that I'm drawing dotted line around. In fact, the idea of the equivalent network is to say, well, this whole arrangement of elements, and it can be as complicated as you want, is represented by a single voltage source called VT, or the Thevenin voltage, and a single resistance called RT. And here are the nodes. Let's give them names, X and Y. So there's node X and node Y. And now once we have calculated what this equivalent network is, we can reattach our resistor R4 and apply the simple Ohm's law to figure out the current. Now the question is, how do you get V Thevenin and R Thevenin? The way you get that is by defining these concepts of open circuit voltage and short circuit current. So let's turn to that issue. First, looking at open circuit voltage. Now imagine that I've already isolated the network and I've drawn that dotted line, and now we're just going to make it a box. So down inside this black box is some network that I want to get the open circuit voltage for. Well, I simply look at the open terminals here and attach a voltmeter. Symbol for a voltmeter is just a V with a circle around it. And I usually like to give little arrowheads at the end here to indicate these are like probe wires attached to the network, and I just measure the value of that open circuit voltage. Now, one thing you might remember about voltmeters is that ideally they have infinite resistance, and so when I attach this voltmeter across the open circuit, it's not going to change anything inside the network. So that's one measurement that I want to make. The second measurement is, go back to the network, and at my open terminal, I want to attach an ammeter, an A with a circle through it. And again, showing the probe points. And now let's imagine that the open circuit voltage turned out to be plus to minus this way, plus to minus polarities. That means a current is going to go through this ammeter in this direction. That current is called a short circuit current because an ammeter ideally has no resistance. And so when you attach an ammeter across two wires, it's creating a short circuit across those terminals. The way you find the Thevenin equivalent, once you have these values, V Thevenin is equal to the open circuit voltage. The Thevenin resistance is the ratio of open circuit voltage to short circuit current. And so now we have the two pieces that we need for our Thevenin equivalent model, VT and RT. And we can attach whatever our load resistor is here and complete the calculation. The advantage of the Thevenin equivalent is that this equivalent network could have, as I showed before, multiple components, lots of sources, lots of resistors, other elements. And all you really have to do is make two measurements at the open circuit, the voltage, and then short that out with an ammeter to measure the short circuit current. So thinking in terms of a laboratory measurement, it gives you a very useful way of figuring out what's inside a gray box that you don't know the details, and you just have those two wires accessible to you. So that's one application. We're going to now turn to another type of equivalent network, and I'll just extend this one by analogy with the Thevenin. The Norton equivalent says that for my active network, and an active network would be one that has sources in it. So we have a network here. I make the same two measurements, open circuit voltage and short circuit current, and what I create now is a current source model. It says I have IN and RN. So here are my nodes X and Y again. Here's X and Y. And the way you get IN is simply to write down the short circuit current, To get Rn, you take the open circuit voltage and divide by the short circuit current. And now you notice this is exactly the same as we had for the Thevenin resistance. Well, this basic equation here relates the two models. If VOC is equal to Rn times ISC, which is Rn times In, and if VOC is V Thevenin, that means I can easily go from one model to the other, from the Thevenin model to the Norton model. If I already have the Norton equivalent and I know these numbers, I just multiply the resistance times the current to get the voltage, and the resistance will be the same. Converting from the Norton model to the Thevenin model is what's called a source transformation. So if I already know VT and RT, and I want to transform that into a Norton equivalent, then the current source here is just going to be, in amps, you know that would have to be volts divided by ohms. So we put in a current source of VT over RT, and the resistance is the same. And then if you just want to dress it up with the proper nomenclature, you call that I sub n for Norton and R sub n for Norton. Well, this gives us one possible way of solving problems where all you're really interested in is the current or voltage for a particular load resistor. Once you have the equivalent network, then you can just reattach your load and proceed with the calculation. Another practical consequence is that you can figure out how to maximize power transfer from an active network into a load. This has application in audio technology. If you are familiar with connecting speakers to amplifiers, you know that one of the standard speaker sizes is a 16 ohm speaker. If you attach that to the output of an amplifier that's also 16 ohms, then you get good sound quality, and the reason for that is that you're maximizing the power being transferred from the amplifier into the speaker. And the way that maximum power transfer issue works is the following. Let's say we already have a Thevenin equivalent model for a resistive network. And what we want to do is find out what value load resistor. The question would be what RL gives maximum P sub L, where P sub L is, let's call it I squared R sub L. Remembering the expression for power in a resistor, this is saying if I know the current going through this load resistor and I square that current and multiply by the load resistance, that tells me the power. Well, what I want to do is consider R sub L a variable. And we want to set up an equation that says, well, what is I? It's just VT over REQ, which in turn would be VT, which is assumed to be a fixed number, and RT is assumed to be a fixed number. But the series equivalent of these two resistors in series is RT plus RL. But now, just to emphasize the fact that RL is a variable, I want to call that X instead, but X is in ohms. Well, let's put that into the expression for power into the load. You've got I squared VT over RT plus X squared times, and now I want to also use the RL symbol here. I want to substitute for X. Well, it's pretty clear now that we've got a function of X. It says we've got X divided by RT plus X squared. And you all know how to find the maximum value of P sub L would occur when the derivative of this expression is equal to 0. So we could go through the details. I would encourage you to do that as an exercise to fill in the steps here. But if I find the derivative, P sub L, dP sub L dx, set that derivative equal to 0, and then solve for x, I would find that my unknown x is equal to RT. So the conclusion is, to get the maximum power transfer from an active network, I would set my load resistance equal to the Thevenin resistance. You can even think of that in an intuitive way. If I have a very small resistance here, the series combination is going to be smaller than it could have been, and therefore I'm going to get less voltage. Think back to the voltage divider. The voltage across the load is going to be VT times RL divided by RL plus RT. So if I make RL very small, that's going to make the voltage very small. If I make RL too big, it's going to make the current going through that too small. So at either extreme, either a load resistor that's too small or too large, I'm going to have less than the optimum amount of power. You get the maximum power, though, at the intermediate value of Thevenin resistance. So that's something to keep in mind, and we'll actually visit that again with an AC circuit equivalent for maximum power transfer with AC circuits. But for a DC circuit, you get the maximum power transfer to the load by setting the load resistance equal to the Thevenin resistance. Now, our next topic is to introduce some circuit solution techniques using resistive circuits, but all of these techniques are also going to apply to AC circuits involving capacitors and inductors. So the first thing is to go back through a technique that you've probably learned before called the loop current technique. Now let's use a couple of voltage sources and a resistive network that would lend itself well to this technique. For concreteness and also for good engineering practice, you should always put a ground in your circuits. So there's a ground, and let's say that we have a 3 ohm, a 4 ohm, and an 8 ohm resistor. The goal of circuit analysis and circuit solution is what I'm referring to here. Solving a circuit means that for each one of these elements, you're finding the current and the voltage. Because once you know the current and the voltage, you can multiply those two together to find the power balance and get all the knowledge you need. The only things we know right now are the voltages across these sources. You've got a guaranteed 10 volts between this node and this node. Potential difference across here is 10 volts. That's guaranteed by the source. Potential difference across this element is 5 volts. But as of right now, we don't know what the current is through the resistors. As soon as we know those currents, Ohm's law tells us that we can calculate the voltages. And if we can figure out the current in this resistor, for instance, we'll automatically know the current going through this source because they're connected in series, and likewise for this combination. So some way or the other, we need to figure out the currents in these resistors. The loop current technique says, let's just assign a current to each of the loops in the circuit, and then write down the Kirchhoff voltage laws. Well, I'm going to use my technique of labeling the polarities of the resistors. Within this loop, the current I1 is going to the right through this resistor, so it's plus to minus, like so. This current I1 is going plus to minus, and we've already got the polarity labeled on the voltage source. For I2, we're going plus to minus through this 8 ohm resistor, the current's going through the 5 volt source, and then for this 4 ohm resistor on the I2 side, it's going plus to minus like so. And that's just a consequence of the direction I set for I2. Clearly, if I had written I2 going in the opposite direction, I'd label the polarities the other way around. Personally, I just prefer to assign all of the loops to be clockwise loops and then just write out the equations accordingly. What I want now are the Kirchhoff voltage laws. For the left-hand loop, or let's call that loop 1, remember what I said before about the Kirchhoff voltage law is that you write down the voltages, writing down the algebraic sign of the polarity sign you bump into first. Okay, so for the 10-volt source, I would write negative 10. For the 3 ohm, Ohm's law tells me the voltage across that 3 ohm resistor is the resistance times the current. So it's 3 times I1 with the positive sign. And now when I'm within this loop 1, I bump into a positive sign here first. I know it's going to be resistance times the total current. The resistance is 4. And then here is the unique aspect of the loop current technique, is that for resistors like this one that share 2 loop currents, you're going to have either a difference between 2 loop currents or a sum of 2 loop currents, depending on the way that you have the loop direction set up. With my setup here, I've got I1 going clockwise, I2 going clockwise, and that means I2 is going up through the 4 ohm, I1 is going down through the 4 ohm. This downward direction matches my polarity sign, my positive sign. So I'd write I1 with a positive sign and then minus I2. Or if you just want to think about it, this is the current going through the 4 ohm resistor. It's the difference of the 2 loop currents, I1 minus I2. Now you know from basic algebra that if we have 2 unknowns, I1 and I2 are the 2 unknowns, then I need 2 equations. So this isn't quite enough. We need a second equation. The second equation would come from loop number 2. Let's start at this node and go around clockwise through this loop. I bump into a positive terminal, so plus 5. I come around here, I bump into a plus sign for the 4 ohm resistor, but now that matches the direction of current I2, so I2 gets the positive sign, and I1 is subtracted from that. So from the point of view of loop number 2, the current going through the 4 ohm resistor is I2 minus I1. Finally finish out the equation with the 8 ohm resistor plus 8 times I2. Now I want to point out, using my polarity convention and writing down the KVLs, notice how the 10-volt source in the left-hand loop shows up in the equation with a minus sign. In the right-hand loop, it shows the 5-volt source shows up with a positive sign. You shouldn't let that confuse you. In both cases, if I'm a positive charge going through this battery in the right direction, I'm going to gain 5 volts. I just happen to have this loop current going through in the opposite direction. And so in these 2 equations, you notice the loop current is going negative to positive through this voltage source, positive to negative through this voltage source. If you prefer writing the equations the other way, then each of these terms would be multiplied by minus 1. So this would be a positive 10 minus 3I1 minus 4 times I1 minus I2 equals 0. It's exactly the same equation, just multiply 3 by minus 1. Now what you would do is continue with this problem and set up the simultaneous equations. 7I1 minus 4I2 equal 10. The total I1's in the second equation. You have negative 4I1. You have 8 plus 4, or 12 I2, equal to, carry this term over to the right-hand side, it becomes a negative. And at this point, the circuit analysis is actually complete. What we have is a well-defined mathematical problem, and what you would want to do is solve for I1 and I2. One thing I'd like to suggest that you do in checking your solutions is, let's say in this example, we use the Kirchhoff voltage laws to set up our equations for I1 and I2. Once we have values for I1 and I2, we're going to substitute into the circuit and calculate the voltages across all the resistors. Well, as a final check, what you can do is sum up all of the voltages around, let's say, the outside loop of the circuit, and make sure that the Kirchhoff voltage law is satisfied for that outside loop, since that's one of the loops of the circuit that we didn't use to set up our equations. Also, what you can do is go to one of the nodes in the circuit, sum up all of the currents, and make sure that the Kirchhoff current law is satisfied. Well, I want to pause now, give you a chance to solve that problem, and check your answers in just a minute. Well, here are the answers that I got from the two simultaneous equations that you see here. I1 turns out to be 1.47 amps, and the I2 value that came out of the calculator, 0.0735 amps. In usual convention is to convert to a multiplier that puts the magnitude in a range of 1 to 1,000. So rather than call this 0.0735 amps, we prefer to call this 73.5 milliamps. Now, the check that I wanted to suggest to you is to use a Kirchhoff voltage law all around the outside loop. So if you refer back to the circuit diagram, I'm going to write down the KVL for the outside loop, and this is what it would look like. If you have the 10-volt source, and then you have the 3-ohm resistor, the only current going through that 3-ohm resistor is the current I1. And then we have the 8-ohm resistor, and the only current going through that is I2. Then we have a 5-volt source, and the question is, what does that total out to be? And when I ran that calculation, what I got was negative 0.002. Now, if you recall, that's supposed to be equal to 0, and that's pretty close. To refer back to the circuit diagram then, what I just did was I went around this outside loop going through the 10-volt, the 3-ohm, the 8-ohm, and then the 5-volt. Now, let's say that I wanted to do a KVL check around this loop. What I would have to use is the actual current going through that 4-ohm resistor. And here's where it's very important to keep the minus signs for I1 and I2. In our example, it turned out that the values of both of these variables happened to be positive. That was just a lucky guess on my part, because it could have gone the other way. And it's important to write down the expression when you're writing the KVL for a loop, write down the expression for that loop. So what I want to do now is check on the left-hand loop, what I was calling loop 1, a KVL check. Once again, we should see the sum of all the voltages sum to 0. In the left-hand loop, I have a minus 10 volt. I have the 3-ohm resistor with just the single I1 current going through it. Then I have the 4-ohm resistor, and I have to remember, from the point of view of loop 1, the expression for the current was I1 minus I2. And now we want to check and see what that value is, putting in the numbers minus 10 plus 3 times 1.47 plus 4 times 1.47 minus 0.0735. And you should check and confirm that that's equal to approximately 0. The point about this checking, twofold. I wanted to encourage you that when you finish calculating an answer, make sure that you have some way of checking whether that's correct or not. And the result that we have just gotten is 0.004 with a negative sign. Once again, that's pretty close to 0. So that's the KVL check. And the other point of interest in this problem is to remember that the loop currents for a branch like this 4-ohm branch that shares two loop currents, the loop currents themselves are not necessarily physical currents. For this 3-ohm resistor, the loop current I1 happened to be the actual current going through that resistor. For the 4-ohm resistor, the loop currents give you just a portion of the answer. You have to combine the loop currents to get the actual physical current going through that resistor. Well, what I want to do now is without actually solving